Right. Welcome to the deep dive, where we, take these kind of like really complex ideas and try to make them hopefully surprisingly clear.
Yeah.
Today we're doing something a little different. We're going to be putting on our philosopher hats,
Yeah.
not just as mathematicians, but as philosophers of mathematics.
Okay.
So our listeners are joining us as we try to unpack something that's really fundamental, the bedrock of mathematical proofs, axioms. How do we know which ones are absolutely necessary?
Yeah, it's about digging beneath the surface of those mathematical theorems that we all learn and love, and kind of uncovering the essential assumptions that make them tick. What are they really saying? And we're going to be diving into a field called reverse mathematics, and it poses this really kind of profound question.
Reverse mathematics.
Yeah.
So instead of, the usual way of proving a theorem using axioms, we're kind of like flipping the script
Huh.
and trying to prove the axioms from the theorem itself.
Precisely. Yeah, so our mission in this deep dive, and we're going to be guided by there's an excellent overview in the Stanford Encyclopedia of Philosophy,
Okay.
the entry on reverse mathematics. And our mission is to figure out how do mathematicians figure out the truly proper axioms for different areas of math.
Okay.
And by proper, we mean both necessary and sufficient. So as we kind of explore this, we're going to be bumping into some fascinating philosophical implications about the foundations of mathematical truth.
So let's jump right into this core idea.
Okay.
The entry highlights this, Harvey Friedman, and his key question: what are the proper axioms to use in carrying out proofs of particular theorems?
Mm-hmm.
And that word proper, it really does stand out to me. It's not just about having enough assumptions to get the job done.
Yeah.
It's about having the exact right one.
That's the heart of it.
Right.
So Friedman, he kind of realized that proper implies this kind of two-way connection. So the axioms must be strong enough to prove the theorem. Right.
But also, the theorem itself, when combined with a minimal set of other basic assumptions, should be powerful enough to derive those very axioms.
Interesting.
So it's this kind of this logical balancing act, if you will.
Right. Like a two-way street.
Yeah, like a two-way street.
They're connected in both directions. And the example that they bring up of Euclid's parallel postulate and the Pythagorean theorem, how does this illustrate the idea of a reversal?
Yeah. So if we think back to geometry, right? For centuries, mathematicians kind of wondered if Euclid's parallel postulates, this famous postulate, was truly independent, or if it could be derived from his other initial assumptions.
And it turned out to be independent. But here's the twist that's relevant to our philosophical inquiry today. The Pythagorean theorem, which we learned as a consequence of Euclidean geometry, and thus relies on the parallel postulate, that can actually be used to prove the parallel postulate itself.
Interesting.
Provided, of course, that we accept those other foundational geometric assumptions. So what this shows us is that within that system, that geometric system that we're working in, the parallel postulate is, in a very real sense, necessary for the Pythagorean theorem to hold.
I see. So it's the fact that we can loop back from the theorem to the axiom. It really highlights the axiom's fundamental role in proving that theorem within a specific framework. It's like the theorem carries the essential logical DNA of that axiom.
Exactly. And as philosophers, we can kind of see this as a revealing a deeper logical interconnectedness than just simple deduction, right? There's more going on here. And the entry also brings up Hilbert's axiomatization of geometry.
Right.
So this is really important. He provided a more rigorous base theory, well-defined set of initial principles within which these kinds of equivalences could be precisely established. And what's important to kind of philosophize about here is that the parallel postulate's independence from this base theory that Hilbert sets up, it underscores that this equivalence that we've been talking about with the Pythagorean theorem, it isn't just some kind of triviality. It's not just that they happen to be true or false together in all conceivable geometries. Their connection is much more specific to the structure of Euclidean space itself.
So it's about pinpointing the fundamental logical dependencies, the very essence of what makes these mathematical truths hold together. And it also mentions ongoing work in geometry by Pambukian that's being driven by uh, philosophical motivations.
Yeah.
So it's like this isn't just ancient history. These questions about the foundations are still driving mathematical inquiry today.
Absolutely, yeah. So this quest to kind of understand the essential logical architecture of mathematics, even in seemingly settled areas, like geometry, it reflects it reflects a deep philosophical commitment, to methodological clarity and logical necessity.
So the second historical example that they bring up is the axiom of choice in set theory. That's a huge one in foundational discussions. How does reverse mathematics approach this?
Yeah, so similar to the parallel postulate, mathematicians like Zermelo, they argued for the necessity of the axiom of choice, to prove certain fundamental theorems in set theory, like the well-ordering theorem. And indeed, reversals have been established within Zermelo-Frankel set theory, showing their equivalence.
Okay.
And Cohen's later work, on the independence of the axiom of choice from ZF, it further kind of emphasizes the profound and non-obvious nature of these foundational assumptions.
But the entry makes some important distinctions between how reverse mathematics treats the axiom of choice and its own, core focus. What are those key differences in perspective?
Yeah, so this is a really crucial point for us as philosophical investigators of mathematics, if you will.
Right.
Reverse mathematics, it primarily concentrates on mathematical structures that can be represented using sets of natural numbers.
Okay.
So, these are countable structures or structures that can be encoded in a countable way. And this actually covers a vast, landscape of what we consider, ordinary mathematics.
Right.
Unlike the axiom of choice, which often deals with sets of absolutely any size or cardinality, and furthermore, the set existence principles that are studied in reverse mathematics, they frequently have this kind of this computational aspect to them, a link to what is definable or computable, which sets them apart from the purely existential assertion of the axiom of choice.
So it seems like the emphasis on countable structures and computability
Yeah.
is really kind of a defining characteristic of the reverse mathematics program, and it shapes the kinds of foundational questions that it asks. This leads us to this concept of the arithmetization of analysis.
Right.
Back in the 19th century. Why is this historical development so critical for reverse mathematics?
Yeah, so the arithmetization of analysis, this was really a transformative period.
Yep.
It essentially rebuilt the foundations of calcula and real analysis, and it kind of shifted them from a reliance on geometric intuition to a more rigorous ground in arithmetic and early forms of set theory. And this involved, redefining these really core concepts like convergent sequences, limits, continuous functions, and even the real number system itself.
Wow.
All in terms of natural numbers and sets of natural numbers. So it was this move towards a more abstract and logically precise foundation.
So instead of visualizing a real number as a point on a line, it's reconstructed using sequences of rational numbers
Mm-hmm.
or Dedekind cuts,
Mm-hmm.
ultimately reducible to natural numbers.
That's right.
It's kind of a huge shift in how we think about these fundamental mathematical objects.
It really is. And Cantor's work with Cauchy sequences and Dedekind's cuts, they both ultimately provide ways to represent these real numbers using the more basic building blocks of natural numbers and sets of them.
Mm.
And this arithmetization, it provided the essential tools and the language for formalizing analysis within the framework of second-order arithmetic,
Right.
which, as we've been discussing, is the central formal system that's used in reverse mathematics. And this allowed mathematicians to start asking more precise questions about the necessary axioms. What do we really need?
Yeah, the entry points out that Dedekind himself, he seemed to anticipate this reversal method with his work on the monotone convergence theorem and the Cauchy convergence theorem. That's a really remarkable insight into the development of mathematical thought.
It really is. Yeah, he demonstrated that these fundamental theorems of analysis weren't just consequences of his his principle of continuity, they could also be used to derive it.
Interesting.
So this early work really kind of beautifully foreshadowed the bidirectional approach that is a hallmark of reverse mathematics. As philosophers, we can see this as an early example of mathematicians really kind of grappling with the essential logical dependencies within their field.
And then we have the formalization efforts of Hilbert and Bernays.
Right.
In their huge book, Grundlagen der Mathematik,
Right.
which is Foundations of Mathematics. How did their project contribute to the later development of reverse mathematics?
Yeah, so Hilbert and Bernays, they kind of took that arithmetization program even further. They developed formal axiomatic systems for arithmetic and analysis, and these systems are direct ancestors of the second order arithmetic systems that we use today in reverse mathematics. And their work, it demonstrated how a significant portion of real analysis could be precisely formulated within a well-defined logical framework. And this kind of continued that move away from purely intuitive geometric reasoning, and they even explored the idea of representing sequences of real numbers using number theoretic functions, which is a conceptual precursor to how sets are used for this purpose in modern reverse mathematics.
So it wasn't just that that arithmetization kind of like changed what mathematics was about. It also provided the tools, the formal language, to ask these really deep philosophical questions about the necessity of axioms in analysis.
Exactly. Yeah. So it's not just the content, but it's the method, the tools that we have available.
And then we get into this intriguing transition from recursive counterexamples to reverse mathematics. This feels like a pivotal moment in the history of this field.
Yeah, it is. So the method of reversals, it actually has its roots in the study of recursive counterexamples.
Okay.
And these are computable mathematical objects that show us where classical theorems break down when we kind of restrict ourselves to the realm of computable mathematics.
Okay.
So mathematics that can be carried out by an algorithm.
Right.
And a classic example of this is the Specker sequence. So this is a sequence of rational numbers that is generated by a computable process.
Right.
And it's bounded and increasing, but it doesn't converge to a computable limit.
Interesting.
Yeah. So there's no algorithm that can spit out the limit of this sequence.
So these counterexamples, they act as like warning signs, highlighting the non-computable assumptions that might be lurking beneath the surface of these seemingly straightforward classical theorems. Exactly. Yeah, they often revealed that for a classical theorem to hold universally, it implicitly required the existence of sets or functions with a certain degree of computational complexity.
Right.
Sets that are kind of beyond the reach of computation. For instance, Specker's work, it hinted that the existence of limits for all bounded, computable, increasing sequences, it implied the existence of sets that were related to the unsolvable halting problem.
Wow.
So this is really deep stuff.
And it also mentions the influence of constructivist mathematics. How did this school of thought contribute to the development of reverse mathematics?
Yeah, so constructivist mathematics, championed by figures like Kleene, Markov, and Bishop, they place this really this strong emphasis on providing constructive proofs, proofs that show how to actually build the mathematical objects, that are being discussed, and the limitations that were encountered within these constructive frameworks, often illuminated by these recursive counterexamples. They kind of further fueled this investigation into which non-constructive principles were truly essential for proving the theorems of classical mathematics. It forced mathematicians to kind of confront the gap between what could be effectively computed or constructed and what classical theorems asserted.
So it's like a recursive counterexample demonstrating the failure of a classical theorem, in a constructive setting that could then be reframed as a reversal, showing that the classical theorem implicitly assumes some non-constructive principle.
Yeah.
That's a really fascinating way of turning a limitation into a key insight.
Exactly. Yeah. The failure of a theorem, when we only allow computable objects, it often pointed to the need for stronger non-constructive axioms to prove that theorem in the broader context of classical mathematics. And the Hahn-Banach theorem reversal that's mentioned in the entry, that's a prime illustration of this connection.
And then we get to Harvey Friedman's groundbreaking talk at the International Congress of Mathematicians in 1974. And this is when reverse mathematics really kind of took center stage as a distinct field of inquiry.
Yeah, that talk was really pivotal. Friedman, he formally introduced subsystems of second-order arithmetic, and most importantly, what are now known as the Big Five.
Okay.
RCA 0, WKL 0, ACA 0, ATR 0, and Pi 1CA 0.
Wow.
And he also presented some initial reversals, demonstrating equivalences between Dedekind's theorems and a principle called arithmetical comprehension.
Okay.
Over a specific base theory. So this was really the formal birth of this program of reverse engineer mathematical foundations.
And they mentioned this earlier, slightly different base theory called RCA that evolved into the now standard RCA 0. What was that? What was the key refinement that led to the adoption of RCA 0 as the standard?
Yeah, so the main difference it lay in the strength of the induction principle that's included in that base theory. So Friedman he initially used a base theory with a more comprehensive induction scheme, but he later realized that the reversals that he was demonstrating could be established over a weaker base theory, this RCA 0, which employs a more restricted form of induction, typically sigma 0,1 induction. So this weakening of the base theory, it was a crucial step in kind of sharpening the focus of reverse mathematics. It showed that these equivalences, they held, even under very minimal assumptions.
And then the field really flourished through the work of Friedman, Simpson, and Smith, solidifying the modern approach and cementing that phrase reverse mathematics in the mathematical landscape.
Yeah, that's right. And Stephen Simpson in particular, along with his students, they kind of undertook a systematic and extensive investigation into the reverse mathematical status of just this vast array of theorems, spanning diverse mathematical disciplines, and this kind of culminated in his highly influential and comprehensive book on the subject.
Yeah.
Which it really has become the standard reference in the field.
So we have this powerful program of reverse mathematics, using the idea of reversals to identify the essential axioms underlying mathematical theorems, and now let's kind of delve into the formal language in which these investigations are conducted.
Okay.
Second order arithmetic and its various subsystems. So what exactly is this formal system?
Yeah, so the language of second-order arithmetic, which is often denoted as L2, it's fundamentally the language of basic arithmetic.
Mm-hmm.
So we have symbols for 0, 1, addition, multiplication, and the less than relation.
Right.
But it kind of expands upon this by introducing this second type of variable, that are kind of intended to represent sets of natural numbers. So we have variables that range over individual natural numbers, but we also have variables that range over collections of natural numbers, along with a symbol to kind of express the idea of membership. Is a number in a set.
So within this language, we can not only make statements about the properties and relationships between numbers, but also about the properties and relationships involving sets of numbers. That really expands our expressive power quite a bit.
It does, yeah. We can construct these formulas that include quantifiers that range over both individual numbers, like for all numbers n, and over sets of numbers, for all sets x.
Right.
And this allows us to formalize a really wide spectrum of mathematical concepts that inherently involve collections or properties of natural numbers.
Now, the entry makes this somewhat subtle but important point that the use of second order in the name can be a bit misleading when it comes to the semantics or the intended meaning of the language that's used in reverse mathematics. Can you clarify that for us?
Yeah, this is a really key distinction for understanding kind of the philosophical underpinnings of reverse mathematics.
Right.
So while the language itself is called second order arithmetic because it allows this quantification, over sets, which can be thought of as properties of numbers, hence that that second order. The way we typically interpret this language in reverse mathematics, it isn't the standard, full semantics of second order logic.
Okay.
So in full semantics, when we say, for all sets X, we mean literally all possible subsets of the natural numbers. However, in reverse mathematics, we often use what are called, general or Henkin semantics, and these are more, akin to the way we interpret first order logic, where the range of our quantifiers can be kind of restricted to a specific collection of sets.
So why this deliberate choice to deviate from the standard, more powerful semantics of second order logic? What's the rationale behind that?
Yeah, so the primary reason is that the central goal of reverse mathematics is to carefully differentiate the proof theoretic strength of various axiomatic systems. If we were to always use the full semantics of second order logic, then stronger systems like second order penal arithmetic would, due to this powerful result called Dedekind's catagoricity theorem, they would essentially have a unique model up to isomorphism.
Okay.
And this would mean that we couldn't construct different models to show that one mathematical principle cannot be derived from a weaker set of axioms. We need the flexibility of having different interpretations of the set variables to kind of demonstrate these independence results.
So by using these more flexible general semantics, we allow for the possibility of having different models for our axiomatic systems, and this in turn enables us to prove that certain principles are genuinely independent of others.
That's right. Yeah. So it's all about creating this framework where we can kind of observe, the boundaries of what each system can prove.
And then the entry introduces the concept of omega models. In these models, the part that interprets the natural numbers is always the standard set of natural numbers, and the models can only differ in which sets of natural numbers are included in their interpretation of the set variables.
Yeah.
And they give this example of REC, the omega model, where the set part consists of all and only the computable sets, and that's particularly illuminating.
Yeah, so we can actually show that certain mathematical principles like the least upper bound axiom for the reals, it fails to hold in this omega model REC, even though a weaker system like RCA0 is perfectly consistent within this model.
Okay.
So this demonstrates that RCA0 is not strong enough to prove that principle.
It's a way of studying the limitations and capabilities of these foundational systems by looking at what holds and what fails in different universes of sets. What are the basic building blocks, the fundamental axioms of full second order arithmetic? Z2?
Yeah, so full second order arithmetic, Z2, it includes a set of basic axioms that capture kind of the fundamental properties of natural numbers. And these are often referred to as PA minus.
Okay.
So it also includes an induction axiom, which in Z2 it applies not just to properties of numbers, but also to properties that are defined using sets.
Right.
But the most powerful axiom scheme in Z2 is the full comprehension scheme. And this scheme, it asserts that for any formula, 5n in the language of second order arithmetic, no matter how complex it can even involve quantification over sets, there exists a set X that contains precisely those natural numbers n that satisfy the formula 5n. So it's a really, really strong existence principle for sets.
And the various subsystems of Z2, including the big five, are created by placing restrictions on this incredibly powerful comprehension scheme.
Precisely, yeah. We obtain these weaker systems by replacing the full comprehension scheme with more limited versions.
Okay.
And the big five subsystems, RCA0, WKL0, ACA0, ATR0, and Pi1CA0. These are the central focus of reverse mathematics, and they're kind of ordered in terms of their proof theoretic strength, meaning that each system in the list can prove all the theorems of the systems before it and strictly more. And the zero subscript in their names, it kind of indicates that these systems typically employ a restricted form of the induction axiom, often just induction for sigma 0, 1 formulas in the weaker systems.
So let's begin our exploration of the big five, the foundational base theory, RCA0. So we know that RCA stands for recursive comprehension axiom. What exactly does this axiom entail?
Yeah, so RCA0, it starts with the basic axioms of arithmetic, and it includes induction, specifically for sigma 0, 1 formulas. So these are formulas with an initial existential quantifier over numbers, followed by a quantifier-free part.
Okay.
But its defining characteristic is the delta 0, 1 comprehension scheme. And this principle, it states that if a property of natural numbers, can be defined in two equivalent ways, both by a sigma 0, 1 formula. So this means we can effectively find a reason why a number belongs to the set, and by a pi 0, 1 formula, meaning we can effectively find a reason why a number does not belong to the set. Then the set of all natural numbers satisfying that property exists.
And that name, recursive comprehension, it really strongly suggests this deep connection to computability.
Yeah, absolutely. So the subsets of natural numbers that can be defined by both a sigma 0, 1 and a pi 0, 1 formula, these are precisely the recursive sets, which are equivalent to the computable sets. So those that can be decided by a Turing machine or any other effective computational process.
Right.
And this is why RCA0 is considered kind of the baseline system. It essentially provides a formal framework for reasoning about mathematics that can be carried out by computation. When we find that stronger systems are needed to prove certain theorems, it kind of signifies that those theorems inherently rely on principles that go beyond what is computable.
Right.
They need something more powerful.
And the entry notes that even within this relatively weak system of RCA0, we can prove some basic algebraic properties of natural numbers.
Yeah, that's right. So RCA0, it's strong enough to establish that the natural numbers, equipped with the operations of addition and multiplication and the usual, less than or equal to relation, they form a commutative ordered Semiring with the cancellation property.
Okay.
So this provides, kind of